Alright, in this video we're going to continue with section 2.1, where we were talking about multiplying matrices, and so we're going to keep going with that and talk about powers of a matrix and the inverse. So the first thing that we're going to talk about here is the powers of a matrix. So this is sort of what it's showing right here, and I know it's kind of hard to see. This is a K. But what this is basically telling us is that when you raise a matrix to a power, it acts very similar to the way that it acts when you raise a number to a power or a variable to power, right? So if you have like x cubed or something, you know that that means multiply x by itself 3 times. Or if we said 2 to the 4th, we know that's just 2 times itself 4 times. And so here we're just basically saying that if you have a raised to the k power, you multiply a by itself k times. Now there's kind of a couple key things here about that. First of all, this definition here is noting that we should have a square matrix, so it needs to be n by n. The reason for that is because we know that if we multiply two matrices together, a times a, then their inner dimensions have to match up, right? And so if a is an m by n matrix, and we multiply it by itself, then we need these two numbers to match. This is what we talked about on one of the last recent pages. And so if these need to match in order to be able to do the multiplication in the first place, then that implies that n equals m. And so that's what leads to a square matrix. So you can only raise a square matrix to a power so that those inner dimensions match. Just to kind of drive that point home a little bit more, let's say we had a 2 by 2 matrix A, 1, 2, 3, 4. We're able to raise A to a power, so if we did like A cubed, for example, that would be A multiplied by itself 3 times, and each one is a 2 by 2. And so these inner dimensions are going to match up. Right? So that's why we need to have a square matrix, so that if we do raise it to a power, we'll have the inner dimensions match. The other thing that we should note here is that what happens if we raise a to the power of 0? Well, it's similar to what we do when we raise a number to 0. So note, when you do a to the 0, you end up with the identity matrix. And I write I sub n because it depends on how big the matrix A is. And so I sub n is the n by n identity matrix. So just to kind of drive that home, if we're talking about this matrix A right here, which is a 2 by 2, if we took this matrix and we did a to the 0, since it's a 2 by 2 matrix, a to the 0 would become a 2 by 2 identity matrix, right? So that would be the I2 identity matrix. And we know that that's the matrix version of the number 1, and so that's why it becomes, when you raise a number to a power, if you did like 2 to the 0, you get the number 1, and so this is the matrix version of the number 1, and so that's why we get the identity matrix when we raise a matrix to a 0, excuse me. Okay, great, so that's how we think about powers. Let's talk about the transpose. So the transpose of a matrix, which is denoted by a raised to the power of t, and it's not a power, it's just a t in the exponent. But anyway, given a possibly not square matrix, m by n, we call the n by m, so notice that this m by n switched to n by m, right? So the dimensions switch. So when you take the transpose, the dimensions switch because the columns of the transpose are the rows of A. In other words, the other way to say that, or the way I think about it, is that the rows of A become the columns of the transpose. And so let's look at a couple examples. Very straightforward to do. The rows just become the columns. And so if this is our matrix A, B, C, D, then our transpose version, row number 1, AB, becomes column number 1. And so that would be AB going down the column, right? And then row 2 becomes column 2. So it would be CD. if that makes sense, I would encourage you to maybe try the other ones on your own. I'm going to go ahead and write them down, but in all cases, the rows become the columns. And in all cases, right, this is a 2 by 3, right? There's 2 rows, 3 columns. Well, the transpose should then be a 3 by 2. That's what this is telling us, the dimensions switch, right? And then this one is a 5 by 2. 5 rows, 2 columns, and so the transpose is going to be a 2 by 5. Okay, take a second to write those down. I'm going to write them down too, but in all cases, the rows become the columns. So here's what B transpose would look like. It'd be a 3 by 2, so row 1 becomes column 1. So 4, 1, 0. Row 2 becomes column 2. And you can see it's a 3 by 2, just like we were expecting. And then if this is C, C transpose is going to be a 2 by 5. And so row 1 becomes column 1, row 2 becomes column 2. I'm going to need to move this over because I didn't give myself enough room here. Row 3 becomes column 3. Row 4 becomes column 4. Row 5 becomes column 5. And you can see we end up with a 2 by 5. Okay. Now in the first one, right, it started out as a 2 by 2. And then when you do the transpose, those numbers switch, but it's still just 2 by 2. So I didn't mention that one just because the dimensions don't change. Okay. So there are a couple of properties related to transposes listed down at the bottom here. The thing I'd like to just note, though, is in everything here, A and B are matrices because we know they're matrices because they're capital, but it also says, excuse me, it also says, let A and B be matrices whose sizes are appropriate for the following sums and products. So in other words, it's saying, like, assume that they're the same size in this one if we're adding them together. Assume that they have inner dimensions that match if we're able to do this multiplication. And so what it's saying is, if you do the transpose of the transpose, you get back to the original matrix, right? Like if you did the transpose of this one and you made the rows equal the columns again, you just get back to the original. This one's telling us that we can basically distribute the transpose to a sum, and so you can distribute into there and they both get transposed. This one's telling us if we have a scalar multiplied by a matrix and we do the transpose, it just transposes the matrix, because when you transpose a scalar, it doesn't change anything. And then this one's sort of talking about when you multiply matrices and do the transpose, you can distribute the transpose, but the order switches. So notice how it was A times B first. Well, when you transpose, it needs to be B transpose times A, because the dimensions switch, and so we need the inner dimensions to match still. These properties here don't come up a lot in our class. These are properties that get used a lot in sort of higher level math classes where you're using where you're doing proofs with linear algebra. And so that's usually where this stuff comes up. But I'd like to just mention that these properties, you know, they're only showing it with 2 matrices, but these properties can be extended to more than 2 matrices. So all these properties can be extended to more than 2 excuse me, matrices. For example, if we had something like A, B, C, D all multiplied and transpose, that's kind of like an application of D where we distribute the transpose but change the order. And so this would end up being DT, CT, BT, AT. You switch the order that they're being multiplied and you give them all a transpose. Alright. So that wraps up 2.1. 2.1 was all about multiplying matrices, raising them to powers, and talking about transpose. And we're going to sort of extend this a little bit more in the next section, where we talk about the inverse of a matrix. Okay. So the inverse of a matrix comes up when it's sort of like the division. When you want to divide matrices, quote unquote, you use the inverse. And so there's no such thing necessarily as matrix division, but you can multiply by the inverse. And so I'd like to start by giving you the idea with just using real numbers. And so, every non-zero number n has some inverse 1 over n, which we can write as n to the minus 1, such that when you multiply those two numbers together, you get the number 1. It's called the multiplicative inverse. So, for example, 2 and 1/2 are inverses because 2 times 1/2 equals 1. Right? So 2 and 1/2 are multiplicative inverses of each other. Now, this is sort of a normal way to write this, but what I'd like to extend to, the way I'd like to rephrase this to make it look more like this expression right here, is you can write 1/2 as 2 to the minus 1. And so the other way to say 2 times 1/2 equals 1 is to say 2 times 2 to the minus 1 equals 1. And so instead of thinking about it like this, because this is sort of like a division thing, right? You divide 2 by 2 to get 1. In this kind of way, you add the exponents and you'd end up canceling them to get the number 1, right? In other words, this would equal, let me rewrite this in a more clear way. If you wrote 2 times 2 to the minus 1, that's the same thing as you would add the exponents, right? There's a 1 and a minus 1, so you do 1 minus 1. And so that's 2 to the 0, which is 1. And so this is just a different way to show you that 2 and 1/2 are each other's inverse. And any non-zero number has something like some inverse, a multiplicative inverse, that gets you to the number 1. However, and every number has that, right? So for example, e, we know that e is approximately 2.71, and it has an inverse too. E times 1 over e also equals 1. Or you could say e times e to the minus 1 equals 1, right? We're thinking about it like this. Okay, so every real number has a multiplicative inverse. But, like it says right here, only some matrices have a multiplicative inverse. And we'll talk about how they exist and how we find them and things like that, but here's how they work. So, if we have a square matrix, so it needs to be square in order to talk about an inverse in the first place. If we have a square matrix and it's invertible, we denote the inverse by this, a to the minus 1. Just like we did a second ago, right? Like 2 and 2 to the minus 1 were inverses. E to the minus 1 are inverses. Well, a and a to the minus 1 are inverses, and so that's how we represent the inverse. And we need them to be square so that we can multiply them together and get the identity matrix, right? And so this is an n by n identity matrix, and a inverse are both n by n, so that when you multiply them together, these things match. The inner dimensions have to match, right? And so that's why we need to have a square matrix. And to remind you again, the I part is the matrix version of the number 1. So we said right here, when you multiply a number by its inverse, you get 1. Well, here, when you multiply a matrix by its inverse, you get the matrix version of the number 1. And so, as a quick reminder, In equals the n by n identity matrix, which means it has 1s on the diagonal, so 1s going down the diagonal of the matrix, however big it is, and then 0s everywhere else. So that's what the identity matrix looks like. Okay, let's talk about some vocabulary and then we'll talk about how we find inverses. So the first vocabulary I'll sort of mention here is if an inverse exists, if a matrix is invertible, so invertible means non-singular. So if it has an inverse, we say the matrix is non-singular. That's not a word that we use a lot in our class, but it's definitely something that comes up in higher level math. If it's not invertible, if the matrix is not invertible, then we say it's singular. So just something you should be aware of. Again, I don't use that phrasing very much, but you might see it in the book potentially. We can see this example show that this matrix and this matrix are each other's inverse. We can see that that's true by multiplying them together and seeing whether or not we get the identity matrix. And so what we're going to do is we'll multiply them like this, we'll multiply them like this, and in both cases we're going to see that we get the identity matrix. And this is also a good opportunity for you to practice your matrix multiplication, which was also learned in the last section. So A times B I'm going to do right here, and I'm going to set it up like we set these things up using a table. And then we'll do another one, we do another color here, we'll do a second one where we do B times A right here. And so let's call this matrix A and this matrix B. I would encourage you to maybe just try this yourself, and again, you should know how to multiply matrices from the last section, so see if it makes sense and see if you can get that okay, and I'll just sort of start writing it down. So remember, the way we do this is you write the left-hand matrix down here. There's my A. And then you write the right matrix on the top here. And then when you do the actual multiplication, you know that you're multiplying a 2 by 2 times a 2 by 2, so the answer is going to be a 2 by 2, right? And this entry, the upper left entry, lines up with this column of B and this row of A. So we're going to multiply the first row of A with the first column of B. And so I'll write out the details here, but it's going to be negative 5 times negative 1 is 5. And then we'll have minus 3 times 4/3. So the 3's cancel and it becomes negative, and so it'll be minus 4. So that's the first entry. And the second entry lines up with the second column of B and the first column of A. And so we dot those two. And so this becomes negative 5 times negative 1 again, so again 5. And then again we'll get, the 3's will cancel. We'll get minus 3 times 5/3. The 3's cancel and it becomes negative, and so we get minus 5. And so that's the first row of the product. And then the second row, this lines up with this row in that column, so it's going to be minus 4. The 3's cancel again, so it'll be minus 4 plus 4. And then last but not least, bottom row, right column, so it'll be minus 4 plus 5. And notice, when we do all those, when we do the subtraction, the addition there, we get 1, 0, 0, 1, which is the identity matrix, right? That's I2. And so this has already shown us that they are each other's inverse, but just for completeness, we'll also show that when we multiply in the other direction, we also get the identity matrix. Now might be a good time to remind you that when you change the order of multiplication, A times B, it doesn't always equal B times A. And in a lot of cases that we talked about previously, one of those may not even be defined if we don't have square matrices. But in this case, since we have square matrices and they are each other's inverse, we can do the multiplication and we should get the identity matrix. But in this case, we put the A matrix up here, so minus 5, minus 3, 4, 3. We put the B matrix over here, minus 1, 4/3, 5/3. And when we do the multiplication here, we get the following. We'll get 5 minus 4 in the first entry, 3 minus 3 in the second entry, minus 20/3 plus 20/3 in the third entry, and minus 4 plus 5 in the last entry. And you can see again, when we do that addition and subtraction, you get 1, 0, 0, 1. And so the takeaway here is we multiplied A times B and B times A, right? We multiplied these on both sides of each other, and we got the identity matrix in both cases, and so they are each other's inverse. And so I'm just going to write that right here. Since A times B equals B times A, which equals the 2 by 2 identity matrix, A and B are each other's inverse. Okay, so that's a good, a nice way to test if two matrices are each other's inverse. But of course, most of the time we want to find the inverse, and so, very few problems say, like, are these each other's inverse? Usually it's find this inverse if it exists. And so that's what we're going to move on and talk about in the next, let's see here, a couple pages. Right. Okay, cool. So the first type of matrix we'll talk about finding the inverse of is a 2 by 2. So this box at the bottom of the page is specifically telling us how to find the inverse of a 2 by 2 matrix. Specifically, if it's not a 2 by 2, we need what's on page 8, and so we'll get to the page 8 for not a 2 by 2, but if it's a 2 by 2 of this form, A, B, C, D, then the inverse, A inverse, is going to be 1 over AD minus BC times this new matrix. And so look at what happened here. The A and the D switched spots, right? So it's DA. And the C and the B stayed in the same spot, but they just became negative, right? So the way you do it is you switch these two, make those two negative, and then you divide everything in the matrix by 1 over AD minus BC. And you can see it's talking about if AD minus BC is 0, then this is 1 over 0, and that's a problem, right? And that just means that A is not invertible. This quantity, AD minus BC, is shown right here. And that's known as the determinant of A. That's an R. Determinant of A. We're going to see more about this in section 3.1, but I should just mention to you now that that's a very specific quantity known as the determinant. Okay, so let's show, here's the matrix A, right? Let's find the inverse of this matrix A right here, and then we'll show that we get the matrix B. Excuse me. So, for example, let's do the inverse of the matrix A right there. So minus 5, minus 3, 4, and 3. Well, what we do is we follow this formula. So we switch the entries of the A and the D. And then, well, let me actually write down this part first. So 1 over AD minus BC. So we have 1 over AD is minus 5 times 3. And then BC is going to be 4 times minus 3. And so that's the fraction part. And then the matrix part, you switch A and D, so 3 and negative 5 switch places. And then B and C stay in the same spot, you just switch the sign on them. So this 3 becomes a positive 3, this 4 becomes a negative 4. And then once you simplify that down, we should get this matrix right here. And so let's do that. So simplifying this down, this is going to be minus 15 plus 12, and so that's 1 over 3. 1 over negative 3, excuse me. And then we multiply it by this matrix, 3, 3, minus 4, minus 5. And when you multiply a scalar times a matrix, you just multiply all the entries by that scalar. And so since it's a fraction, you just divide each one of these things by negative 3, right? And so we end up with minus 1, minus 1, 4 thirds, 5 thirds. And that was the exact same thing that we had up here. And so we just found the inverse that we already knew existed. And again, we know an inverse doesn't exist if this quantity AD minus BC right here ends up being 0. And so it's helpful just to see if that equals 0 before you do one of these problems. Although you obviously realize it pretty quick here when you have 1 over 0. Okay. So that's finding the inverse of a 2 by 2. And before we go any further, I would just like to show you why inverses are useful, or how they can be useful, before we talk about finding more advanced inverses. And so that's what's on the next page, and that's what I'm going to start with before we talk about inverses of bigger than 2 by 2s, because the inverse of a bigger than 2 by 2 is actually not that bad to find. So let's talk about how we use this first of all. So there's a typo here, I just noticed. This tells us if a matrix A has an inverse, it gives us another way to solve the matrix equation. And so this should say AX equals B. Sorry about that. So if we have a matrix equation and we know the inverse of A, then we can solve this equation pretty easily. And so here's how. If A is invertible and it's square, then for every B the equation ax equals b has the solution x equals a inverse b. And so if we want to solve this equation for x, the solution is this, right? This is what this is telling us. And let me show you why. So, proof. Why is the solution of this just multiplying the inverse on the right-hand side of b? So let's say we have an invertible matrix. So suppose A is a square invertible matrix. And let's suppose we want to solve the equation ax equals b. Well, we can take the equation ax equals b, and we can just multiply on the left by A inverse. Let me actually move this b over so that we can multiply on the left a little more easily. Right, so we want to solve ax equals b, and so we can multiply on the left-hand side of both sides of the equation by the inverse. And we're assuming it exists, right? So suppose A is invertible, and so A inverse exists. Well, on the left-hand side here, these two things multiply together to give us the identity matrix, right? That's what the last page said. When you multiply A times its inverse on either side, you get the identity matrix. And so A times A inverse right here just equals IN. And so what we really have here is we have the identity matrix times X equals A inverse B. And anything times the identity matrix just stays the same, right? The identity matrix I sub n is the matrix version of the number 1. And so this just equals X. And so what we really have is X equals A inverse B, which is exactly what the theorem above there tells us. And so this gives us a nice way to solve equations, and this is the way that a lot of computer programs solve linear systems and things like that, by multiplying by the inverse. I'd like to just point out, though, that it's important that you multiply on the left, right? We need to multiply A inverse on the left of A because the dimensions need to match up. In other words, if you multiply on the right, and you had like B times A inverse, well, B is an n by 1 matrix, and A inverse is going to be square, n by n. And so these inner dimensions are not going to match, and so you can't multiply on the right. Not only will it not give you the right answer, but it's not even possible to do, right? And so this doesn't make sense, which is why you need to multiply on the left. All right. So let's look at a specific example of how this can be solved with a very simple 2x2, and then this same idea can be extended to big matrices too, right? The matrix in this is just some arbitrarily large square matrix, so it could be really, really big, and this property and this result still holds. And so let me just show you, like in this system, how we can solve this one then. So this is a system that we can write as AX equals B in the following way, right? This is like something that we learned early on in the course here. So this can be written as AX equals B, where A is the coefficients, right? So the A would be 1, 2, 3, minus 6. The X would be X1, X2. And the B is the constants, 9, 3. And so we want to solve the system for x1 and x2, and yeah, we can row reduce and things like that, that's fine. But let's do it using the inverse instead. So we can just find the inverse of A, and then multiply it on the left by this one, and then that'll be the answer, right? And so this is a good chance for you to try the inverse. Usually if I do this in class, I stop here and let people do the inverse of this one, and so I think it'd be helpful for you to maybe try the inverse of this. So this inverse is, use the formula on the last page. I would pause the video right now and see if you get the right answer. I'm just going to kind of slowly walk through it otherwise. So the inverse is 1 over AD minus BC, so 1 over minus 6 minus 6, so 1 over minus 12, times, switch the A and the D, So minus 6 goes here, 1 goes there, and then you make these two. So you switch the signs. And so this simplifies down to, you divide all these things by negative 12, right? So it simplifies to 1/2, 1/6, 1/4, negative 1/12. And so what we want to do is this is our inverse, this is A inverse, right? And so we want to multiply on the left by this. And on the left is an important thing there. Multiply on the left to solve the system. And so I'm going to rewrite this system with this multiplied on the left. I'm trying to show you all the details here. So let's take this right over here and do it. So A inverse, what we want to do is A inverse times A times X equals A inverse times B. Alright, so that's where we're heading right now. And so A inverse is what we just found. 1/2, 1/6, 1/4 minus 1/12. A is the original matrix we started with, 1, 2, 3 minus 6. X is just x1, x2. And then on the right hand side we have A inverse, 1/2, 1/4, 1/6 minus 1/12. And then B, 9/3. And so the idea here is these two things are each other's inverse, right? This is A times A inverse, and so these two matrices just cancel into the identity matrix by 2. In other words, what we really have is 1, 0, 0, 1 times x1, x2 equals the right-hand side there. And when we do this multiplication, you multiply the 9 multiplies the first column, the 3 multiplies the second column, right? So we'll end up with 9/2 plus 3/6, 9/4 plus minus 3/12. And then on the left, right, you're multiplying the identity matrix times x, so this just stays the same. And then, so in other words, this just equals x1, x2, which is the answer. Well, that's what we're interested in finding. And then what's on the right-hand side is the answer. And so when you add those two things together, you get 5. And when you add those two things together, you get 2. And so the solution of this thing is 5, 2. And we found it using the inverse rather than row reduction or something like that. And so again, it's a really nice way to solve systems sometimes. Computer programs oftentimes use this to solve systems. Let's finish off this page with a couple properties. Again, these are kind of properties that don't necessarily come up a ton in our class, but when you move into higher level math and you want to do proofs with matrices, things like this come up pretty significantly. So the first one's telling us if A is invertible, then that means the inverse is also invertible, and this is saying, what this says is the inverse of the inverse is the regular matrix, right? So if you find the inverse of something that's already an inverse, you just get back to the original, which should make sense, right? The second one is very similar to the thing on the last page, the transpose thing, or 2 pages ago. It's similar to this ABT equals BT AT. So that was something from page 5 here, right? We saw this property on page 5, and this one is very, very similar to that, except it has the inverse instead. But notice that you distribute the inverse to A and B, and you switch the order of them. And then the last one's talking about doing the inverse of a transpose. So if you do the inverse of the transpose, it's the same thing as the transpose of the inverse. And I'll just remind you, for AT, that's something that we just learned, that is all rows become columns. All rows of A, I should say. of AT. So again, just some nice properties that apply using concepts of inverse. Not something that comes up a lot in our particular class, but definitely something that you might want to keep in mind moving forward. All right. Let's talk about finding the inverse of a matrix bigger than a 2x2. Like I said, it's pretty easy. It's something we use our calculator for. And so if you have a graphing calculator, it'd be nice to pull that out. If you don't have a graphing calculator, you should have some way to row reduce, either on your phone or the internet or some app or something. And so you will want to get that out here so you can practice doing this, especially on the next page where we do some activity. Okay, so here's the idea here. Here's the theorem. So we've got a square matrix, right? It's n by n. A square matrix is invertible if and only if, right? So this is a double-sided implication again, so it works both ways. If and only if A is a row equivalent to I sub n, and I'll just remind you once again, that means the identity matrix. And, so first of all, we know a matrix is invertible if it row reduces to the identity matrix is what that's saying. And what it says here is the sequence of row operations that changes A into the identity matrix changes the identity matrix into the inverse. And so the way we find the inverse of a matrix, and this works for 2x2s as well, but it works for any matrix, which is nice, is the algorithm for finding the inverse, right? You put A and the identity matrix in a matrix together, row reduce it, and then it should turn into the identity matrix in the first spot, so A will transform into the identity matrix, and then the identity matrix will transform into the inverse. If you don't end up with the inverse there, then that means it's not invertible, so A wouldn't have an inverse. And so I realize this is maybe, as I'm reading this, maybe not the most straightforward statement here, so let me just rephrase this and tell you the process. You put A and I into a matrix together. You use a calculator or some other row reduction technique to do row reduced echelon form, and when you do row reduced echelon form, you'll get the identity matrix where A used to be, and then the inverse will be where the identity matrix used to be. And so this ends up being the matrix, the inverse, excuse me. If you do that, if you put A and I into a matrix and then you do RREF, and you get not the identity matrix in the first spot and anything else in the second spot, then that means the inverse doesn't exist. Okay, so let's do a couple. It's really straightforward to do, right? So let's find the inverse, if it exists, of these matrices. And so this is our matrix A. Let's see if it's got an inverse. Let's put it into a matrix with the identity matrix. Let's do AI. And so that would be this. 1, 2, 3, 2, 3, 4, 4, 2, 1. There's A. And then I'm going to put it into a matrix with the identity. 1, 0, 0, 0, 1, 0, 0, 0, 1. So there's A. There's I. What the theorem at the top of the page tells us is that the operations that change A into the identity matrix change the identity matrix into the inverse. And so if we just put them in a matrix together and we do RREF, RREF is going to try to put a pivot here, here, and here. And so it doesn't even like mess around with I at all. It's going to focus on A, but since I is in the matrix with it, whatever row operations you do here are also going to be carried out over here, and so it's going to transform I into A. So I just want to write that down. So what the theorem says is the operations that will change A into the inverse, into I, will also change I into the inverse. And if you don't change A into I, that means the inverse just doesn't exist. Okay, so it's very straightforward. You just do RREF and see what happens. So this is your opportunity to try that. So I would remind yourself how to do reduced row echelon form. If you need some help with that, I'm happy to remind you about how to do that. Just send me a message, we can meet. But I'm going to assume you know how to row reduce on a calculator or something, so I'm just going to do RREF. So I put this into a calculator, I row reduced it, and I got this. So A turned into I, right? So that means the inverse exists, and whatever ends up over here is the inverse, and so it turns out to be this. And so the idea is A reduced to the identity matrix, and so this is the inverse. Oops, sorry, I didn't realize off the screen there. So we just row reduce A with I, A becomes I, and I becomes the inverse. And you can always double check this. I won't show the details, but you should be able to check, because if you multiply A and the inverse, you should get the identity matrix. And so if you did 1, 2, 3, 2, 3, 4, 4, 2, 1, if you multiplied that by the inverse, 5 minus 4, 1, minus 14, 11 minus 2, 8 minus 6, 1, you can double check that you do get 1, 0, 0, 0, 1, 0, 0, 0, 1. And so you can verify that you did find the identity matrix, right? You should be able to do A times the inverse and get I. And that's how you do it. Again, this works for any size matrix. So this will work for a 2 by 2. The nice thing about a 2 by 2 is that we just have a nice formula for it. So this formula from page 6 is just saying, hey, if we've got a 2 by 2, you don't need to row reduce anything. You can just use this formula to find it. This is telling us, no matter what size matrix you have, you can put it in an augmented matrix with I, row reduce, and that'll switch the identity matrix into the inverse. The second one is just an example of where it doesn't work, showing you how not every matrix has an inverse. So let's try to find the inverse of this matrix. And so here's A, another color here. Here's A. I'm going to put it in a matrix with I, and so I'm not going to rewrite it. I'm just going to try to wipe that out and put it in with 1, 0, 0, 0, 1, 0, 0, 0, 1. So I'm just putting it in a matrix with I, row reduce, see what happens here. So when I do RREF, and you can verify this yourself here, but I get the following. 1, 0, 7 thirds, 0, 1, 5 thirds, 0, 0, 0. That's what A turns into, and then I turns into this. Again, I just did this ahead of time to not waste time in class. You're welcome to double check that you get this. The important thing to note here is that A, which was this, did not reduce to the identity matrix, right? In the one before, the A became I. It didn't happen here. So this is showing us, since this is not the identity matrix, this means that this matrix A is not invertible. So A did not reduce to the 3 by 3 identity matrix, and so A is not invertible. It's singular, if you will. And so that's how we find inverses, excuse me. And again, that works for any size matrix, regardless of whether it's 2 by 2, could be a 10 by 10, could be a 20 by 20. It'll always work the same. Alright. So there's about 30 minutes left in our period here. We've talked for about 45 minutes, and there's an in-class activity on the next page that I usually let people work on in groups. Let me just put that page up here. What I'd encourage you to do is to try to work on some of these problems yourself, or at least think through them. Think if you know how to do them. Think about how to start them. I would usually give people 10 or 20 minutes to work on these and then go over them together. And so since there's 30 minutes left in the period, I would strongly recommend you do that. I would recommend you pause this video right now and see if you can do these problems. The ones on the top here, you should be able to do using a formula. So these are 2x2s that you can do kind of easily. This one you should think about whether or not an inverse even exists. The inverse of this one you would want to put into a matrix with the identity matrix and row reduce, just like we did on the last page. And then on the last problem here, this is a linear system. Let me set up the linear system just to make it more clear. This is a lot like what was on page 7 here, right? It's kind of like this problem where we're going to solve a system by multiplying on the left by the inverse. And so this is the linear system. 5, 4, 10, 7, x1, x2 equals 1 minus 2. And so you would find the inverse of this. This is a, right? This is like ax equals b. Find the inverse of this one, multiply it on the left by this, and that would be the answer. So again, there's still a half hour left in this period technically, and so I would strongly recommend you try those. Just pause the video right now and give them a try. What I'm going to do in just a moment here is I'm going to put up the solutions and just walk through them rather than me writing them all down and all that. I'm just going to put them up and sort of talk through them. And so I'm going to do that right now. So pause the video and try these on your own. And wait just one moment. I will put up the answers here. Alright, so here are the answers. I really hope you took an opportunity to try those. Online classes can be particularly challenging. I'm trying my best to make it as much like an in-person class as possible, but that requires you to buy in and actually try these things. So I really hope you gave that a try. Here are the answers. So the inverse of this one doesn't exist because we need a square matrix to have an inverse, right? It needs to be n by n is what we said, and so this is not a square matrix, and so it's not invertible. The other two are 2x2s, and so we're able to use the formula on page 6 here, this formula right here, that we used previously. And when you do it on this one, right, that's the formula. You end up with this right here. AD minus BC is 35 minus 40. You switch the D and the A. You make the B and the C negative. And so that's the inverse of that one. This second one doesn't have an inverse because when you do 1 over AD minus BC, you end up with 1 over 24 minus 24, which is 1 over 0. And so this, this part of the formula is 1 over 0. And so that's just showing you that there's no inverse. The second one, you put A in a matrix with the identity matrix, just like we did on the last page, and you row reduce. This thing changed to the identity matrix, which means that this is the inverse. And so that ends up being the inverse, right? This is just this right here. And then lastly, to solve this system here, we find the inverse of this, which this is the inverse of this one right here, by the way. And so we already know this inverse. And so I'm taking that inverse from the previous problem right at the top of the page, and I'm multiplying on the left by both those things. These two things just cancel, and you're just left with this on the left. And then when you do this multiplication, you end up with this, and when you do that subtraction, you get that as your answer. And so that's a nice way, again, to solve a linear system by using matrix inverses. Okay. Thank you very much for listening. I'm available for questions. Please reach out if you would like to meet.